Cool. So this is going to be like an hour-long discussion. And please use, you could use the slide as well, but also if you can just ask and put questions over here, that will be great. So again, a little bit of reiterating the context of this symposium. The main deliverable for SAG21 for this study analysis group, it's a report to NASA by mid-2021. And as you already saw, both on the overview talks and on the scheduling of the topics of the contributed talks, they were all attached to certain topics covered by the subgroups that we have within SAG21. Now, given all the talks, we basically compiled a little bit of information or what we gained from all of you from here, and we divided it basically in 3 topics which encompass these subgroups. So the first topic that we wanted to put up for discussion is this sun as a star idea, in which so the main 2 points are the following. So first, it was obvious from the very first talks that studies from the sun are extremely informative, and especially for model testing and validation. So, you can see the talks from Kopp, Cuscioli, Santos, Mayorga, in which you saw that, using the sun as the ground truth, it's like an amazing resource that we should definitely take advantage of. But also we got some very nice talks on the dangers of approaching in that direction or from extrapolating from the sun, because we need to be careful with assuming the sun as the star, like as the proxy for everything. Because of course other stars are different and it's difficult to validate over there. Spots might not have same sizes, shapes, and properties. Sorry, like for example, this talk by Maria Schutte, in which she was seeing these huge spots on other stars, other like sun-like or sun kind of star. Same talks by Panja, Kostogris, Wedemeyer, in which evolving on the models from the sun for other spectral types might get a little bit different. And also how the properties might actually evolve differently with stellar type or properties. So, this goes all the way back to the overview talk by subgroup 1, in which they mentioned this faculty dominated evolution as a function of time. But we wanted to open the floor here a little bit in terms of any other points that you want to make in this sun as star studies and on both the improvements that we could do in our models with this, but also the dangers of extrapolating from the sun. By the way, Ben, maybe you want to say something on this as well?
Yeah, I'm taking notes from the discussion. I posted that in the chat there. And mostly what I want to convey is that we're using this as our opportunity to synthesize some of the lessons that might have emerged from the last 2 days. And if there's anything you felt that we need to emphasize in this report or a point that hasn't been explored enough, this is our opportunity. So I see we have a hand raised from Nuno.
Go ahead.
Go ahead and unmute yourself.
Yep. Well, thank you. I just had a comment on this point of, the sun is a nice testing bed, but it's not all the stars, right? That's of course true. Let's not forget that we still need, I think, from what I understand, to really understand the spectra of the sun in the different regions. And this can be used, one, to calibrate the models, right? So that's important. And on the other hand, future missions like Plato, they really want to detect Earth-like planets around solar-type stars, solar, G-type stars. And so at least for those cases, it will be, I think, fundamental that we use the sun to really understand what's going on.
Right, yeah, I totally agree. And I wanted to bring also here the, stellar and solar astrophysicists in the crowd into, I was, when I first heard, for instance, of this evolution from spot dominated to faculty dominated as I think this was one potential explanation to changing variability as a function of age from Kepler light curves. But I wanted to ask, put the question out there, how certain are we about that? Can we do any further studies to investigate that? You know, what would be the best venue for stellar folks to, you know, really pin down if this can be a function of spectral type, for instance. So you look at the Slido, there was, I mean, the most popular question is, how does that evolution from spot to faculty dominated, how much of that applies to M dwarfs? Because, you know, Kepler is like a biased sample in FGK stars. So it probably didn't went down to M dwarfs. So you wanted to bring that question out there. Heidi, I see your hand raised. Please go ahead.
Yeah, no, I just wanted to say that indeed the study that I showed was only from K0 to F6. So I mean, solar-like going quite cool, but not to the M dwarfs. And there was also the comment from Sasha that simulations, based on simulations, it looks like in M dwarfs the faculae would be darker. On the other hand, I mean, this is not a new result, even though the paper I showed was relatively new, but it was already in 1998, I think, Radic, who first showed that, I mean, there is a change from younger stars that are spot dominated to older ones that are faculae dominated. But so it really seems that this happens, but this is based on quite small number statistics still. And I mean, really knowing all the details, I mean, we still have work to do, but it seems that this change really happens.
Right. And yeah, I mean, it might be I think this is the beauty of doing this interdisciplinary work, right? Like this is the kind of results that you folks, you know, we know about this from like 20 years ago, but at least I had no idea until a couple of years when I saw this Kepler paper, for instance. So this is the importance of this exchange over here, I think.
No, and I think it's really interesting. And I mean, I've been wondering how we could get a better handle on this, but I mean, no firm conclusions on that yet.
Right, and I think, I mean, the work that we're doing within SAG21 could be like a starting point. I don't know, maybe there has been other starting points. Of course, we're not the first to sit down and talk to each other, I presume. But the report could focus on that as well. You know, the need that could be one of the, I don't know, findings or important points to make, especially in subgroup 1, which will be like, you know, we need to talk to each other or find the venues to sit down and make these exchanges. So we're all on the same page, let's say.
Yes, certainly. I mean, I think there have been several attempts to talk to each other, but it's good to have more venues for that.
Yep. Ben?
Yeah, related to that, I just wanted to say that if there is a specific observation folks have in mind, like some of them that have come up today, please make sure that Néstor and I and Elisa Quintana and Rob Zellum are aware, because a section of the report, as you know, will focus on future observations that can help in this field. And while we don't make recommendations to what NASA may do, we can point out observations that would be useful, and then it might just be that NASA decides to support gathering those observations at some level.
Yeah, and also I think I can see how this could improve, say, your retrievals. If you know that it's, to say, an old star and should have more faculae than spots, or this ratio could be constrained at some point, that could help, you know, in the priors that you put in these retrievals by a ton. Also, all these, you know, spectral decomposition techniques as well could inform so many of these techniques that I think it's extremely useful to have this information. Okay, so I think we're on the same page, at least in the Isonasa star, which was the first thing that we wanted to bring here.
There's one
the second
from the comments, Néstor.
Yeah, go ahead.
Heather Segla points out that the sun as a star measurements are also a great way to characterize instrument systematics, especially if we get different instrument baselines overlapping. I think that's important because, for example, POET as a using espresso, which is also being used for exoplanet observations. It would be great if we could gain two pieces of information from this type of observation, both the astrophysical information about the sun and any information on systematics with espresso.
Yeah, that's a very good point. And also it touches upon Laura Mayorga's talk, checking the how good the detectors are going to do, how deep we can go to the noise floors and not confound ourselves between noise and the actual signals. So yeah, I totally agree with that point. Very good point. Okay, the next slide that we compiled here was related to the star spot properties. And we spoke a ton about this, both from different techniques, both from different assumptions even. And we captured these two main points here in dark gray. Well, the first is, occulted and unocculted features provide extremely useful information to constrain star support properties. And the next one is that, however, work still needed to incorporate study degeneracies in normal. So on the first point, I think it was evident from a ton of the talks, that current and upcoming facilities are able to extract these properties, at least to observe, to get data from these features, both from photometry and spectroscopy. You can go back to the talks by subgroups 3, 4, 5, talks by Giovanni Bruno, Matthias Malun, Ignacio Rivas, Chima Magruder, and Panwar. All of them, they highlighted how you can extract this information from actual data. But now in terms, when it comes to interpreting it, that's the second point, there's still some unsolved issues. It was evident, for instance, that single band photometry is just not enough. You can take this information from subgroup 4 or by Ignacio Rivas or Matthias Malun. And that, multiband and spectrum monitoring encodes both active region contrast and covering fractions, which is a cool constraint, but it might have some degeneracies involved depending on the data set. By all these talks, from Rivas, Malun, Magruder, Garcia, Dodson, all of them showed, how you can extract this information from multiband and spectrum monitoring. Now, I found it really interesting from the talk by Giovanni Bruno, at least, and others also mentioned this, of course, which is that even, our occulted spot models need to be validated. Even if you see these occultations by the spot, there are some degeneracies that appear there. Even with very precise instruments like digital GST, you will still see some degeneracies with spot size and shape. And I presume that that's in the case, even assuming circular spots, what happens with the most confusing shapes that we see in the sun. And the latest point here is that information could even come from activity indices, but might be hard to map depending on what is needed. So this comes from both the talk of Dos Santos and Dori, that while it might be useful for student observations, getting the global picture, at least in my mind, and this is our Ben and I's conclusions, so they don't have to represent the absolute truth, of course, but from my view, at least, it seems like if you don't have, you really need a ton of data to validate these different data sets against themselves. Even within transit spectroscopy, when you see these offsets, for instance, to be honest, the first time that I saw the WASP-19 data from Access, when we took the transit spectroscopy, I was not very convinced that it was, I was maybe thinking, could this be systematics? Could this offset between different nights could just be systematics and nothing related to the star, really? Even the transit spectrum that we got when we saw the TIO feature, I was, maybe this is systematic. So I went back to the data, but then seeing so many data sets from other places really helped, nail down that this is something that is really happening in WASP-19, for instance. And I see this same thing happen over and over again with other data sets as the works that were shown here. So I think this confluence of different data sets is extremely important. There's not a silver bullet to tackle this problem, in my view. But again, wanted to open the floor on this particular topic.
We have a question on Slido, and
go ahead.
I think it's for everybody here, from Yvonne. And she asks, are we being a bit optimistic about spot properties in terms of degeneracies? She's not sure that we can do it without ab initio modeling backup?
Yeah, I mean, I don't have a strong opinion on this other than yes, I mean, oral mores are wrong. There are only some of them that are useful, but yeah. Yvonne is here, I suppose.
I think she might have had to step away. I
Right.
would say this also actually gets to the next slide in some ways, which is when we're talking about retrievals, the current retrieval approaches I think are quite optimistic because we're stretching stellar models far beyond where they were meant to go by using a model calculated as the spectrum of an entire star to say that this is the spectrum of a star spot. A star spot just looks like a star with a different temperature. And even further, one of the really interesting points that's come out of the discussions from SAG21 is that stretching those models to represent vacuoli is quite a bit more of a stretch. That there's some unique features that show up that are relative to these active regions that aren't really encapsulated by modeling it as a star of a hotter temperature. And so I'd like to hear from folks that have more experience than me, more expertise here, about the most promising ways forward to getting models of vacuoli spectra.
Yvonne, I see her in the chat actually. Oh, sorry, in the Zoom.
Yvonne says that she has some noise going on, so she can't
no worries.
talk. But
Right.
but we answered the question. Or Néstor.
Right. Okay. So I think the main confusion that I have in my mind is that whenever people talk about like ab initio models or these simulations, I mean, the only ground truth, the real ground truth in which we can actually get, these actual observe these features, in my mind, it just comes the sun and maybe some close by giant stars for which we could get some interferometry and measure this stuff. But my fear is that I think it's the constant, of course, fear of, if we create these very complex models, how do we find ways to completely test them and be sure that we're not just biasing ourselves with sun properties? Heather, raise your hand.
Yeah, I thought I would just chime in on that particular point right there. So one way that we can potentially test these models on stuff other than the sun, in particular things like 3D MHD simulations, is to actually use the planets to probe and spatially resolve the star. So I have a paper from 2016 that talks about a new way of looking at the Rossiter-McLaughlin effect and using photometry to normalize your ground-based spectra so that you can do a direct subtraction of out of transit minus in transit and isolate the starlight behind the planet. And in that paper, we show comparisons to that local spectra behind the planet along the transit cord to results that we got from simulating things with 3D MHD simulations coupled with 1D radiative transport to simulate. I think in that paper, we did 3 different iron lines at like 3 or 4 different magnetic fields. So it's a way to validate these simulations on stars other than our sun. So I think that's something we could keep in mind is ways where we can look at particular observations and actually validate the simulations and say, look, we know they work very well for the sun, and okay, we will probably never be able to validate them as well for other stars as we would for our sun, because we can really properly resolve it for our sun. But there are a couple ways that we can use the planet. And Dana Stravins has some work on that, kind of showing similar stuff as well, using the planet as a probe of the star.
Right. Yeah, this is also great synergy, of course. Like, we're using all these techniques started like to try to characterize the planets really, but it's beautiful how we can actually get information from the star itself with this, for sure. Cool.
Yeah, and I think it's a way to, like if the planet occults an active region, then we can then actually probe the active region directly, by doing these differential measurements of out minus in, in a similar way to transmission spectroscopy, but really focusing on characterizing the star in particular. And if you have simultaneous photometry, that helps you to really decide like, okay, what you're seeing in active region does it have a contrast variation that looks like a faculae, or does it have a contrast variation that looks like a spot? And then you can go back to the local CCF behind the planet and look at the net convective blue shift variation and see.
Right.
That's kind of what actually reminds me of one question that I had for the transmission spectroscopy people is everyone is kind of using these 1D Phoenix models and assuming this temperature difference, which I guess doesn't take into account the fact that there is a net convective blue shift that happens if you're in an active region. Is that incorporated at all when people are using these Phoenix models? And if not, what extent could that be impacting your results?
The answer to the first one is no. People just use, the Phoenix model that they have from Husserl et al., and that's it. No shift. And the second answer, I have no idea. I haven't tested this. I don't know if someone in the call has before. Yeah. One question though that I have, I totally agree with you. Like, the optimal thing would be to go with the occultation. Try to measure like an RM. To take an RM measurement while in occultation, but trying to time those two, it's extremely difficult because with unraised telescopes, you have to apply for time. You have to be extremely lucky that just you got the occultation. Wouldn't that, like, if we really, really wanted to do that, and we concluded that was the way of doing this, wouldn't that call for like a dedicated instrument almost that could monitor like these very active stars to try to do some kind of RM survey? I'm thinking on stars like HAT-P11, like WASP-19, for which we know that they're constantly we constantly see occulted features. I wanted to hear both about this from observers and theoreticians as well. Guli?
Hey, can you hear me?
Yeah.
Cool. Yeah. Yeah. Great themes here. Thanks, y'all, for organizing and following up on that question. What about? I mean, at some level, using the planets themselves is a great idea. We should absolutely do it for tomography. But at some level, they're hard, right? Because they're small and the relative sort of tomographic size is sort of small, which has benefits. But why not do more like eclipsing binaries, for example? Maybe they have bigger signals anyways, and you can sort of, the spectrum of the two stars relatively better. You can disentangle them. It has different trade-offs, so it's not a slam dunk, but certainly something useful. And in that sense, you wouldn't necessarily have to do point and stare observations, which are quite costly, but you could just do sort of in and out of transit snapshots, for example, and do sort of like a starry decomposition type approach. And then sort of on the other question about like, what about convective blue shift, I feel like there's almost like a culture clash of like people who think about extreme sort of heavily, profoundly spotted stars and folks who focus on maybe less spotted stars or assumed to be less spotted. And essentially, in one case, you're dominated by suppression of convective blue shift, and you're sort of just looking at the pure RV effect. And in the other, there's like truly a discernible second spectrum just attributable to that extra emission from the spotted star for the spot itself. And I feel like there's some sort of chasm that we haven't crossed that somehow is related to Ben Monte's paper of trying to map out exactly where that transition occurs and as a function of spectral type. So this is sort of touching on earlier conversation here. So I don't know, I'm sort of just connecting some of these themes and being a little unspecific at this point. But I guess my key idea would be that doing tomography in a systematic way with eclipsing binaries, I think has lots of value, and you can do it more cheaply than like a dedicated, like we're going to have a telescope that just does this. Like you could just put it in a queue.
Heather.
Yeah, just to comment on the eclipsing binary side of things, I think it's a really good idea and something that should be exploited. But the upside is, you know, you have a bigger thing that's doing the occulting, so you have more signal to noise in that sort of local region you're trying to look at. But then the downside is that you don't spatially resolve as finely. And so if you were wanting to look in depth at what the limb dependence is, if you only block out like half of your star or a quarter of your star, you're not going to really finely resolve those changes that happen at the limb, which might be important for your transmission spectroscopy, especially as really close to the stellar limb is where you get quite a few extreme changes.
Right.
But still definitely some benefits to looking at EBs, but just to keep that in mind is all.
Also from, from an observational perspective, even I'm just having a hard time thinking of like this snapshot idea, which yes would be cheaper, but it has also its downsides on the amount of information that you could gain. Well, okay, but that's food for thought. Yeah. All right. Any other comments or questions on this topic of star spot properties, which seem to be okay? So we can move to the next and last slide, which does not mean that the discussion ends there. I mean, if someone else has something else to bring up, that's fine. Which is this planet plus star retrievals.
Oh, go ahead. Sorry.
Yes. Go ahead.
Before we go on, I think there's one relevant question on Slido from Vatsal Panwar on how activity indicators could be different for younger free main sequence stars like T-Tauri stars compared to more mature stars. And I'm guessing in the context of the spot properties, if this is something we need to keep in mind.
Right. Wouldn't this also be related to this evolution from spot dominated to faculty dominated, for instance? Also, I don't know how sizes change. Maybe some of the stellar folks can come over and help us out on that.
Yeah, I don't think either of us are really qualified to comment on that, but it is a very interesting question. Oh, we have a raised hand from Heidi Korhonen. Please, Heidi.
Go ahead, Heidi.
Yeah, am I unmuted now? Yeah, I think
yeah.
I am. Yeah, I mean, it goes to the same that, I mean, with active stars, I mean, when the stars are young, they are rapid rotators, and then of course the dynamo works better. So as long as you have rapid rotation, you have lots of magnetic fields, and then you have larger spots, and you also create the polar spots that some people have discussed. So I would say that, I mean, T-Tauri stars are, I mean, similar to young active stars. I mean, they are just a bit younger, and of course the convective zone might be, I mean, is deeper. So there are some differences, but I mean, it's still, they are typically T-Tauri stars are very magnetically active and have spots, but might also have bright spot features if you still have, I mean, accretion going on. So you might have bright accretion spots too, and things like that, but they are very variable.
Right. And how much of, well, I mean, I think we're going back to the very first question probably, but how much of this is applicable to, well, this theory is applicable to M dwarfs? You know, we speak about dynamos, and I'm not even sure M dwarf, you know, to what point they do have these same processes going on.
Well, actually, I mean, yeah, I mean, the solar dynamo should be sort of an alpha omega dynamo, so turbulence and difference of rotation. And of course, with fully convective stars, I mean, people thought that it would the dynamo operation would change, but at least they seem to follow the same activity rotation relation as I was also showing in one of my plots, where you had the X-ray luminosity and the Rossby number, and it had both partially convective and fully convective stars, and they seem to follow the same laws. On the other hand, from observations, we tend to see that M-dwarfs are more flaring and maybe don't show as much photometric variability. But again, I mean, there seem to be all kinds of observations depending on which M-dwarfs you exactly look at. So it's difficult.
Need more data.
Always.
All right, any other questions in this Slido? I cannot see the Slidos, that's why I'm relying on you folks, or Ben, really.
No, we're good on Slido. There's some conversations going on now in our chat about an upcoming paper, which will talk about different activity indicators, how they perform for M-dwarfs.
Okay, cool. So okay, let's jump to this last slide that I had here regarding the planet star retrieval. So the main 2 points here is that, of course, like the first point is current data, and this is why, you know, what's triggered SAG21 really is that we had data to say that it was going on, but we do know that current data is being impacted by stellar contamination, and likely future data from GWST will as well. You know, both from HST and ground-based transit spectroscopy data currently being impacted by this. Talks, you know, by Panwar, Dos Santos, Edwards, Garcia, really, also the talk by subgroup 2. I mean, there's plenty of data around to see that this is a thing that has to be taken care of. Then that leads to the second part, which is that incorporating these in retrievals is, you know, not straightforward. I mean, there are models out there and we are doing retrievals, but there's some subtleties that we still don't understand. I put 4 here, which might not be like a comprehensive view, but those 4s were touched upon at least within the talks here and the symposium. The first one is that there are important differences in stellar models, even if no magnetic fields are assumed, which might impact on joint plus planetary retrieval. So, you know, talks by subgroup 2 with Meyer, and other talks as well that we saw from Kostogris as well, in which they were showing how all this changes. Also the talk by subgroup 1, how spectra change if you add like magnetic fields, just like a different thing. The second one related to this same point, which is spectral models of spots faculty are needed, not clear how to validate them against stars other than the sun. This involves some of the discussions that we just had. You know, Rossiter McLaughlin might be a way to go. Also binaries to do it in a more coarse, not a located resolves, not spatially resolved necessarily, but it would be a good start. Talks that touch on that point is Kostogris, Panja, Cristioli. Then the third point is related to, you know, the stellar rotation and active region evolution, complicate efforts to stitch data from multiple transits. That's you know, one of the main complications here. Talks by Malun, Panwar, Edwards, Garcia, Berger, and more that touch on that same point. And very important point touched upon by Drake Deming as well. And, you know, even in the case in which you have no spots, there's some stellar well, really it's a model contamination, to be honest, but it's from the star. That there's a resolution linked bias that needs to be incorporated. And I was left wondering in that same talk on how, you know, we're really, I mean, with GWST, folks are going to try to go to 10 ppm precisions, right? Like we're getting crazy in terms of the precision that we're demanding of these huge missions. And, you know, what if you have spotted regions that also have their own internal, you know, variations in high resolution that we're not capturing? You know, how could that maybe impact on here? That might be a bit pessimistic. Maybe Drake has something to say there.
Well, I think we need to understand the high resolution, the spectra of all components at as high a resolution as we can, or at least as at a resolution that resolves the lines. So
Right.
we see the line structure.
Right. So Espresso, you know, this poet mission could be a really good starting point on that, perhaps. Well, with the sun.
Well, that's for the sun, yeah.
Right. Yeah. All right. Any comments on this, especially from the retrieval folks? I see, I'm gonna put people on the spot here a little bit. I was seeing
Right.
Ryan McDonald.
We have a
but-
hand raised from.
Oh, Leonardo, go ahead.
Yeah, I have sort of a provocative comment for our community. And this alludes to something that I asked in Slido before. So from the practical point of view, it's very difficult to schedule simultaneous observations, which is one of the things that a few people have proposed to do with activity. Especially when you're trying to coordinate space-based and ground-based observations, it can be very difficult, near impossible. And what I was wondering is if our community can organize ourselves to create the sort of network that we can help facilitate the coordination of these simultaneous observations, especially from different facilities in different countries, different hemispheres. Maybe a particular target is not accessible from the northern hemisphere where we have most of our facilities, and then we need to go to the south, and then the south. Anyway, I wonder if we can actually do that in the future. We would definitely benefit from it, but it depends on ourselves to take the initiative.
Yeah, no, definitely. Like coordination is key, especially in these very hard to schedule observations, and they're expensive as well. I mean, an RAM observation with espresso is no easy feat to schedule and to propose for. But yeah, I agree. Kind of what TFOP does sometimes. Like we're gonna observe the transit of X. Why don't if you have access to X facility, maybe you can be you can do photometric monitoring, you can do some RAM effects, some extra transits to measure transit depth variations, etc. But I agree, like a network in that sense would be awesome.
Yeah, I wonder if we can do that for GWST, for instance. Have a
right.
Not well, it wouldn't be called the ExoFOP, but it would be called, I don't know, web something.
GFOP. Right. Yeah, I think that's a good idea actually. To try to plan ahead and coordinate between the different observatories around, because I mean, and also this benefits the institutions themselves and the programs themselves. So I'm sure like all the folks that do photometric monitoring, they will be happy to join forces with some of the PIs of the programs that are going to be released in the GWST once the accepted proposals are in. Same thing goes for ground-based high resolution instruments. I keep thinking Espresso. I'm sorry, I'm so biased. The name is so great, and I'm so decaffeinated right now. So I think it's a very good idea indeed to coordinate, given all these unknowns.
And I think that's something that we could point out in this report to NASA, that an ExoFOP-like network for coordinating complementary James Webb observations could make better use of the actual James Webb data.
Right. And it will also make them contemporaneous. I mean, how many times have you got like a transit spectrum and have wished like, oh, we should have done high-res spectroscopy, we should have done multiband photometry. So, it could transparent all this. So I think that's a great idea. Yeah. All right. I don't have any other points here to make. I don't know if you, Ben, I think we literally covered all the talks, at least in information-wise, within these points made here, which are, of course, not extensive of everything that has to be touched upon. But
we have a comment from Gully.
Yeah.
Hey, yeah, I guess one thing on the planet star retrievals that I'm not sure if it was mentioned, but that I think is really valuable is now that like automatic differentiation techniques are available, they allow you to move to many more parameters than we've been used to. And so I think it is hypothetically feasible when combined with GPUs to do the sort of thing that we heard from Deming, which is to sort of jointly model at high spectral resolution everything, like essentially your entire spectrum, the spots, and like all the parameters sort of that you want for your planet. And I'd point to the Radis framework, which is relatively new framework that's incorporating the GPUs, but there's some discussion on there about experimenting with AutoDiff also, so that you could actually build onto that the full sort of PET profile and everything that you want for your planet. So I see that technology all is still pretty far away, but certainly there is a path to doing, you know, what everyone wants, which is like the full thing at full res.
Right. I think this also enters on the, I mean, I know our conversation previously was pretty observationally focused, but I think you have a very good point in that there's computational and theoretical techniques that could also benefit from such a coordination in you know, performing, you know, full models of exponent host stars that are going to be observed, say, by GWST, in order to constrain all this. So yeah, that's a very good point as well.
Yeah, maybe I just add that the key technology that I think NASA should, not saying what NASA should invest in, but that NASA could hypothetically invest in is like I mentioned, AutoDiff, but specifically the Hamiltonian Monte Carlo and the so-called no U-turn sampler, but specifically applied to retrievals. The problem with that operationally is that you have to redesign all of your retrieval frameworks with AutoDiff from scratch. Which is pretty expensive. So, but it's possible. And I feel like there's, I feel like that'd be a worthwhile thing to do.
Yeah, I think, you know, the Bayesians in the crowd might scream back that, well, but we cannot compute evidences, but there's some good step samplers as well, which in this Bayesian frameworks like nested sampling that could use these AutoDiff techniques to compute also the Bayesian evidences. So I totally agree with your main point, like, you know, algorithmically.
Yeah, that's right. In fact, you can combine both of those techniques. Yeah.
Yep. Great. So I don't know if there's any other comments in the Slido or the chat. Ben, can you double check?
I don't see any, but I would like to hammer on my point that it's not my point, but a topic that has come up a couple of times that is really interested in me now is that there seems to be a prime limitation seems to be an understanding of faculae or bright magnetic active regions. And I say that because as Ryan McDonald pointed out in the overview talk, there's a few examples now where these retrieval frameworks are inferring the presence of unocculted active regions to unocculted bright active regions to depress the optical transmission spectra. And then a really interesting thing that's come out of conversation with the folks in subgroup 1, our stellar and heliophysics experts mostly, is that the technique we use to model spots or to model all active regions by just tweaking the temperature of a stellar model is maybe okay for spots, but it's a bad approximation of faculae spectra. And so those two things are concerning me now, our lack of understanding of faculae spectra and the increasing evidence we see for faculae in data. So I was just wondering if people with more expertise could talk a bit about how we might solve that issue and get good model faculae spectra. And I know we had relevant talks, but I'm not sure if our speakers are still here.
Yeah. I
Hi,
don't think. Oh, go ahead.
Sorry. Hi, this is Sami. Maybe to the faculae. So the one star where we have a good understanding of them is for the sun. Obviously, for the sun, people are not looking usually at the very broad spectral ranges, at least resolved, that you need for stars. So you need to fill that in with computations. And MHD simulations are doing a pretty good job of that. So you can reproduce lots of different observations from there. And you can compute with these MHD simulations also faculae on other stars. Don't think there is any big magic to that. This has been done some years ago by Benjamin Bake, who was a PhD student here, and who unfortunately left science. In the meantime, we know things that go beyond what we knew at that time. For example, that you don't have such a thing as a purely hydrodynamic cool star. You just don't. There is always going to be, because convection is very turbulent, there is always going to be a turbulent small-scale dynamo working, even if you don't have a global dynamo. Yeah, even if your star is non-rotating, as soon as you have convection, you're going to get magnetic fields. And so that's sort of your zero state. Yeah, it's not zero field. There will always be a field. And for the sun, that can be quite a lot. That can be 60, 70 Gauss. And then you have to build up your faculae on top of that. And so that, I think, is going to be another frontier, because what we look at as the quiet photosphere of the star may actually not be completely quiet. But going into the faculae after that, once you've built this up, I think is not going to be such a big deal. And we can do that, at least for main sequence stars. Going towards, let's say, giants is going to be challenging, because the convection becomes very strongly turbulent, very strongly supersonic. You get shocks all over the place. It's doable. It has been done. But it's going to be challenging to do that properly, and also with the faculae.
Right. I think the issue there would be how to include that in some sort of retrieval. So you need like a fast computation of all this, and you cannot, I presume, do like MHD fast. So
No,
you would have to map or interpolate from MHD simulations, right?
Sure. Yes. Yeah, that's what you would have to do. So you would, you start with a very rough grid, and then with time you make it finer and finer. And this is what the Stagger people did with their 3D things, but that was only hydro. And we are just in the moment starting to build up something like that with the MHD, including the faculae. And Mayuk, who gave a talk yesterday, Panja, he's starting to do that with spots. So I hope a couple of years down the line, we'll have a much more complete picture.
Thank you for that, Sami. Heather?
Yeah, I would just add to that and echo everything that Sami said there. I totally agree with that. And in particular, to draw attention to the significance of the different magnetic fields. I mean, for example, one thing again is this net convective blue shift. It changes as a function of center to limb, and how that varies as a function of center to limb is very dependent on the magnetic field. Just as one particular example. So we definitely need to be exploring that magnetic dependence. And then I would add to that is, like, at the moment when we're doing the sort of 3D MHD stuff and coupling it with the radiative transport, we're still largely looking at individual lines. So being able to get and look at thousands of lines like we do when we are looking at sort of exoplanet data would be very useful. And we still really need to empirically validate this in terms of observing faculae at a large wavelength range. So to my knowledge, if you have a wavelength range that's similar to something like what you would do if you were looking for exoplanet stuff, like 380 to 700 nanometers or something, I think there are still no faculae observations even on the sun looking at that. That's something that I think Nuno Santos proposes to do if POET is able to come up. And like, I think the FTS in Göttingen that can do pointed sort of staring and can, possibly do some of this in the future. So there are, and like the Lars spectrograph is another one that can kind of do this, but it maybe at a more limited spectral bandpass. But I think even just sort of probing faculae at larger bandpass on the sun will be important. And then of course, moving that to other stars when we can.
Thank you. Yeah, that's great input. Thanks, Heather. Sven?
Yes, I was just wanted to add that all these 3D simulations, of course, and also the radiative transfer in as part of the simulations, and also for this spectrum synthesis to produce observables, that of course is computationally really expensive. And I think it would be in the best interest in this connection to maybe define a list of priorities of what would be most important to focus on first. Also, when you do these 3D simulations, like these local simulations, then the magnetic field is usually a free parameter. I mean, how you start with that, right? It's just not just one model. I mean, it's like a whole new degree of freedom there. So just to summarize this, I think detailed discussion maybe in the first group would be important to define priorities for that.
Yeah, and I think that links very well with this idea of like a coordinated effort, because we don't, of course, we would love to understand all the stars out there, but we do have like a ranked list, right, based on the exponent host stars that are going to be observed, or that have already been observed. So if focus could be on those kind of stars, that could constrain the parameter space, as you say, into what do we want to characterize in detail. Great, loving all this input. Thank you, folks. Is there any other comment or question folks want to make in the chat, Slido, or even here, raising their hands?
We have a clarifying comment from Ayuk Panja on this topic, that we often forget that spots are 80% penumbra and 20% umbra, and the penumbra can be hotter by 700 to 800 Kelvin. So this common approach that we have of modeling a spot spectrum is, again, a simplification, and it might be better and more accurate to use two stellar spectra to model the impact of a spot, which has both umbra and penumbra.
Right, especially, and this is a very good point. And also it's very relevant. Again, I'm going back to Maria Schute's work on these giant spots. Like, someone might say, spots in the sun are small, so maybe it's not that, but then we go to other stars and we see these huge spots that, these contributions might be even more important. So I agree. That's a very good point.
Svetlana is here. I'd like to add a comment maybe here. I'm not sure it was mentioned. I had to leave for an hour or so. This spot filling factors, spot sizes we talk about, we emphasize several times they depend on the wavelengths, of course. But that dependence is often due to dependence on the height in the atmosphere. And so the size of spots also, and the appearance of spots depends on the height, and the temperature of spots depends on the height where we look at. And there was a paper by me and Nadina Fram, 2019, I believe, for M dwarfs, where we actually saw the change of the filling factor, so it means size coverage, of spots with the height. And that also, it's kind of, one can think simple-mindedly that this is all taken by wavelength, but it's not necessarily taken by wavelength. So that also one needs to keep in mind.
Yeah, this is right. In reality, it's a much more complicated problem than what we're using. So yeah, we might want to explore where
exactly it's a
complex
phenomenon.
Yep. Thank you for that comment, Smetana. It's very important as well. All right, we're approaching the hour. I wanted to go to the next slide, which is basically a thank you slide. First of all, I want to take the opportunity to thank you everyone for joining this discussion. It was really useful. It's going to definitely be going into the SAG report. If you want to be included in that report, please just shoot an email if you're not already in there. It's the first thing. Second, I want to thank people organizing here, the chairs. Thank you very much for helping us chair the sessions. You did an excellent job. I was amazed by how all these turn out, given that it's virtual. I'm not very fond of virtual conference symposiums in general, but I love this. I learned a lot. I want to thank the speakers. You folks were amazing. The kind of science you're doing is extremely exciting and very relevant to our report and to transit spectroscopy in general. I want to thank Ben for helping co-organize this symposium. It was a crazy idea we had, turned out to be really good. I think we did okay. And thank you everyone for joining and for being part of this symposium, both with your inputs, both sitting down here, and of course to our subgroup leads, which have been amazing, doing a great work, spearheading each of the topics on here. So yeah.
And big thanks to Néstor.
Thank you. Yes.